Okay, hello and welcome back to AIAIART. This is lesson 8 on neural cellular automata, so one I've been looking forward to for quite some time. So I'm really excited to get into this, but before we do, I did want to acknowledge that a lot of this work, even more than usual, builds on some previous work done by a few specific people. So Alex Mordvintsev and co have worked on these cellular automata and related work, and a lot of the code and ideas in today's notebook are going to be drawn from that. So I thought before we even dive into the notebook itself, it'd be worth just taking a look at one of the key papers that inspired all of this, and to see, use it as kind of inspiration and a goal for where we'd like to get to over the course of the lesson. So this is that paper. It's on distill.pub. And for me, this is really kind of the gold standard in terms of communicating research. Everything is interactive, everything links to the code, and it's all incredibly well explained. So I'd recommend just having this open in a second tab while we go through the notebook. We'll come back and look at particular sections once or twice, once we start talking about the model and the training. But the idea here is that they're setting up a cellular automata that is we'll talk about what that is, but for every pixel here, it's just seeing its immediate neighbors, and yet it's able to, they're able to sort of coordinate and grow these shapes, and they're somewhat robust to perturbation. So really, really neat project. We're going to sort of take this, play with it, build on it. But I just wanted to highlight this paper right at the start as just the most incredible resource. And actually everything they've written, this link here is for all the other work that they've done on that topic. So highly recommend checking that out. But today we're going to build up to that, and we're going to start at the real basics and then sort of see how we go. So if you haven't already, you can save a copy of this notebook in your Google Drive, run it along with the lecture. Now in this one, I'm just going to be kind of skimming through the notebook and giving an overview. If you'd prefer something longer with a more sort of conversational style and questions from Twitch chat and so on, I will also link in the description of this video a slightly longer recording of the live stream where we had, going through running the code, editing it, and so on. So I think that's about an hour long. This video is hopefully going to be much shorter, but it'll cover the same topics. Okay, that's enough introduction. So let's start with what is a cellular automata, right? What are these things that we're dealing with? So hopefully, at least some of you will have some familiarity with this idea. It's quite popular in certain circles, but if you haven't, the core idea here is that we're going to set up a bunch of sort of individual units or cells, and these are often represented by pixels in a grid or on a line, but it can be sort of different arrangements. And the idea here is that instead of some sort of global system, all that a given cell can see is its immediate neighbors. So this example here is from Conway's Game of Life. And in this case, there's an update rule, right? So the cell can see its neighbors and it can change its state. And in Conway's Game of Life, this very particular famous cellular automata, if it has 4 or more neighbors, it'll die due to overcrowding and stay dead. If it has 3 neighbors, it'll come back to life. If it has 2 neighbors, it'll stay alive. But if it's got too many or too few, if it's all alone or surrounded by additional living cells, it'll die. So a very, very simple set of rules, but you get these beautiful complex behaviors out of this. And in fact, once you start digging in, it turns out that the system is incredible. It's Turing complete. You can see people build computers within Game of Life that themselves can simulate Game of Life. Just really kind of mental stuff. So yeah, go check out the website to play with the rules in action, or see this YouTube video here. Hidden behind the mouse, this YouTube video here for a deep dive into what you can do. But this is going to be kind of the common theme when we talk about cellular automata, is you have these relatively simple individual units with fairly basic rules, and yet you get some pretty incredible emergent behavior. So that's convolutional. That's cellular automata in general. If you're looking for more resources, there's tons of videos on YouTube. This one here, this 30-minute video, is a great exploration by an artist who's been playing with different types, exploring the space of possible rules and so on. So really, really great rabbit hole to fall into if you haven't already. But today we're going to be looking at a kind of subset of the possibilities. And specifically, we're going to start with something that I call a convolutional cellular automata. And so for this section, the inspiration is this Neural Patterns website. So neuralpatterns.io, it lets you load and run various rules and presets that have these really simple rules, and we'll see what the rules look like, and yet they create some sort of fairly interesting behavior. So in this particular case, the rule, we don't have a yes or no, on or off kind of situation. Instead, we have a continuous output, and that continuous output is defined by some filter, right, which we're going to convolve with the image. This is how the cell perceives its neighborhood, along with some activation function. And so without playing too much on the site, let's see what it looks like in Pytorch. We need some sort of grid, some world for these things to live in. So we can do that just by creating a random 32 by 32 pixel world. Then we're going to start with a random kernel. And this is our 3 by 3 sort of window. Again, this is for an individual cell. It's going to look at, in our example here, look at its immediate neighborhood. What is its state? What are its neighbors' states? And use that to update. And so in our convolutional case, the kernel is going to define how much we weigh each individual cell in the neighborhood. We're going to sum those values, and then we're going to pass them through an activation function. And you can use whatever activation function. In this demo here, just the tan-h function. And so to get our output, we're going to convolve our kernel with our grid using this conv2d function from Pytorch. And that's going to give us our output. And we can have a look at what that looks like with a bit of matplotlib. So you can see here's our grid, right? Our 32 by 32 pixel world. And for each of these cells, we're looking at the neighborhood, the 9 cells or 8 cells around it and the cell itself. We're multiplying those with this kernel. We're passing the result through that activation function that we've specified, and we get this output. And so this is the sort of minimum viable implementation of this convolutional cellular automata in Pytorch. And it's nice, it's really fast. This convolution operation is really well suited to running on the GPU. And so we can run a bunch of these simulations in sequence. But to make things easier from the code side, before we actually do that, we're just going to wrap the same idea in a class. So you can see here the code is pretty sparse. Most of this is just documentation. But we can initialize one of these convolutional cellular automata. We can specify the kernel size. We can optionally sort of scale up or down the individual values in the kernel. We can decide what activation function we'd like to use. And it's going to set that up. And then when we call the forward method, we're going to take our kernel, convolve it with whatever grid we pass in, and then pass the result through our activation function. So in practice, it looks something like this. We create an instance of this class. We apply it to the grid, and using it like a function here, ca brackets grid, this is just calling the forward method because we inherit from nn.module. And you can see that the output is the same shape as the input. So this is that same operation we saw in this demo, just now using a class to keep things neat and tidy. And if you want to see what this looks like applied a number of times, there's a few little utility functions defined way up in the setup section. So if we head back up here, you can go and read the code, see what that looks like. But this is basically just saying, take a grid, run it through a given convolutional cellular automata a number of times, and save the results. And so this is nice and easy for quick previews. So we can create a random one here, and we can call render, and we'll see these little previews at different steps. And you can run this a bunch of times. Each one will have slightly different properties because the kernel and everything is initialized randomly. But we also, while we do this render process, save every frame, every grid state to a steps folder. And so we can kind of preview what that looks like in motion. So I highly recommend, running these 2 cells a number of times, seeing what kinds of variety you can get. Sometimes the videos are a bit flickery, or the motion is really slow or hard to follow. So this additional demo here is just saying, well, we can save every 5 frames. We can average them so that the flickering is reduced, and we can get kind of a sped up video. So for some types of behavior, this is really useful for pulling out something interesting. But we're not going to dwell too much on this. There was just one more demo I'd like to show, which was a particular pattern, again, shown first in that video by the guy behind this neural patterns site. And so this takes a different activation function, right? The so-called inverse Gaussian, which we can implement here in Pytorch, and combining that with our sort of convca class and a hard-coded kernel. So this is, a particular instance of one of these convolutional cellular automata. We can render that and see what it looks like. And this is the video that I used in the announcement for this lesson. And we polled people to say, how many parameters do you think you need to get this kind of complex emergent behavior. Some people said more than 1,000, some people said about 100. There's only one guess for 10, but yeah, if you count up, okay, we have some repeats in here, so you could say it's even fewer, but 9 values in this kernel, a couple of parameters in this inverse Gaussian function, but really very little is needed to specify a system where, repeatedly applied to a grid, we get this kind of lifelike and interesting emergent behavior. So like I said, this is the theme of today's lesson. You get this really cool kind of complexity even out of these simple systems. And so you can play around in this section as much as you like. If you want to see what the kernel of a given, once you've done a random one, right, up here, creating a new CA is equal to CompCA, it's going to create it with a random kernel. You can inspect that kernel, you can tweak the values manually, you can set them up, and so you can kind of explore and see what different kinds of patterns you can get, what sort of outputs you can create. But yeah, quite fun to play around with. So this is step 1. This is the first part of our journey. And you'll notice it's really cool, but there's some kind of shortcomings which we'll address coming forward. So number 1, depending on how we pad, we sometimes get weird effects around the edges, which we don't like. Ideally, we'd wrap around so that the grid has no kind of discontinuities. And then the other thing, all of these updates happen at once, which if we're starting from a random grid, is not obvious what it's doing. But sometimes if you start from a completely uniform starting state, you're not going to ever get anywhere interesting. And this also implies that there's some sort of global synchronization. And when we're talking about, these systems in terms of analogies to biological systems, right, actual cells in a brain firing, or microorganisms in algae communicating, there's no global clock to keep everything in sync. And so we'd like to get around that and start moving away from this kind of unified single update. You can also see, well, these are only single channel. They only have a single continuous output. So we'd like to kind of build on this, make them, more complicated, maybe have some learnable parameters. And so that's exactly what we do in this next section here. We'd like to create some cellular automata that can self-organize. We'd like to have, learnable parameters so that they can have, steerable behavior. We'd like to do the circular padding, randomized updates, and we'd like to find a way of training them. So again, this is building on a lot of Alexander Mordvintsev's work. In this case, the code itself comes from the implementation from their micro NCA texture generation with ultra compact neural cellular automata. A really cool paper where they show how even systems with a very small number of parameters can learn to try and replicate some pretty complex textures. It's a really, really nice paper, really nice demo, and we're going to kind of take that and build on it. So we're going to start with a very simple implementation and then extend it. And we'll also add our own flavor. A big theme of this course has been seeing what we can add text guidance to. So of course we'll also add clip. But let's look at our architecture here. So before we had this ConvCA class that just had a filter that was initialized randomly and applied that plus an activation function. So we're now going to step things up in a few ways. Number 1, we'll take in multiple channels, right? And in this first example, we'll have 4 input channels specifically for R, G, B, and A. Then we're going to specify 4 filters, and we could have the filters themselves be a learnable parameter. But in this case, we're just going to hard code them to a few sort of standard filters. And then for each filter, we'll multiply it by the neighborhood for each channel. So we have 4 filters, 4 channels. That'll give us 16 inputs, which we're then going to feed through a very small neural network to produce our 4 outputs. Remember, there's 4 input channels. We'd like to update the cell at the center of each of these little grids here in the diagram. So we're going to pass through our 16 inputs that we get from our filters. We're going to feed them through a hidden layer with some number of neurons, and then an activation function, and then a final layer is going to produce our outputs by combining these according to some learned weights. So this is what it looks like in code. Again, hopefully this is not too hard to pass. We have our hard-coded filters. We specify the number of channels is always going to be 4 for this first example. And then this section here is our little brain. Let me just hide the form. And if you want a discussion as to why this is equivalent to a linear sort of system here, you can go and check out the video that's linked in the next section on a Pytorch implementation of the original paper. But in essence, we're using these kind of one-by-one kernel convolutions to just apply this little linear sort of final layer in parallel across a whole grid, make it nice and efficient. But this is computationally equivalent to setting up a sort of more standard Pytorch MLP with linear layers. Okay, so we have our little brain, and these are going to be the parts that have learnable parameters, these two convolutional layers. We can optionally zero out the weights to keep things sort of more flat and stable in early training. And then in our forward pass here, what we're going to do is we're going to take in our grid, we're going to apply our filters convolutionally, one channel at a time. So that's what this per channel convolution function does. And then we're going to take that, this is the output of our filters, pass it through the first layer of our network, pass it through an activation function, pass it through the second layer of the network. And then instead of applying this is now our predicted update, instead of applying this everywhere, we're going to randomly apply this in only some places, right? Defined by this update rate. And so this is now stepping away from that global clock that I talked about earlier. It's adding a bit more randomness into the system, and it's saying only, in a given iteration, only particular cells are going to fire or update, depending on what analogy you're using. So that's the core of this class. You can see it's a little more complicated than the convca class we saw. And then it also has some additional functions here. So 2RGB is just mapping our kind of native representation, which is usually between -1 and 1, mapping this into something that looks more like an image. We have some utility functions for making videos. We have a seed function for setting up an initial grid. And in this case, we're going to set that all zeros, but you'll see later how we can modify that. And then finally, we have this mystery function here, which we'll come back to shortly. So we can create an example here with 8 hidden neurons, and we can check the parameters. So we said 4 channels, 4 filters. That gives us 16 inputs to this little neural network brain. So the first layer here has 16 inputs, 8 output channels. There's also 8 bias parameters. And then our second layer has 8 inputs coming from the first layer and 4 outputs, which are now the sort of predicted updates for the 4 channels. So we can create this. It's going to be random initially, but we can apply it repeatedly to a grid. This is very similar to the previews we were doing before. And generally, depending on the random initialization that you get, you'll see some things that are quite cool. But we'd really like to be able to steer how these perform. We don't just want to start randomly and hope for something interesting. We'd instead like to encourage specific types of behavior. So now we come to the fun bit, actually training these things. Like I said, we'd like to add some text guidance. So we're going to use the style loss as introduced in this paper, but we're also going to add our own clip loss, which is using clip. Quick reminder, clip is a model that's been trained to map both images and text into the same space so that we can compare them. So this little demo here does just that. We take 4 random images, 3 pieces of text, and you can see they map to each sort of input, whether it's an image or text, gives us a 512 dimensional vector. And we can compare those to say how similar is a piece of imagery with a piece of text. And that's what this code does. You can go and check it out. But the ultimate sort of upshot of this is that we can take our text and we can score an image based on how closely it matches that text. And this is all differentiable, so we can use this as a loss function. Likewise, the style loss, this should be familiar if you've done AIAIART lesson 2. We're going to use the early layers of a pre-trained convolutional neural network, right, VGG16, and we're going to compute some features from that and use that to measure how well sort of texturally and stylistically 2 images match. And so in this case, we can set up a style image. This is going to be our kind of target. And so in our training loop, we'd like to optimize towards the text description and the style of this style image. And you can replace this with whatever you want. So if you're following along, now would be a good time to start this next section running, right? Set it going, maybe tweak the prompt, try a different color or some other description. But while that runs, let's take a look at the code itself. And then we'll see how, although this does look very similar to the training loops you've seen previously, there's some additional tricks happening. Okay, so here we're setting up our prompts, right? These are our kind of targets, setting some parameters like the number of iterations, how many hidden neurons we have. We're creating our cellular automata network, setting up an optimizer to optimize its parameters. And then here's sort of innovation number 1. This one's not really important, and in this case, it doesn't even come into play. But sometimes we'd like to start with a fairly high learning rate and then reduce that after some number of iterations, so that we can, kick off the training at a higher learning rate and then refine it at a lower learning rate. So that's all this learning rate scheduler, this multi-step learning rate scheduler does. Every milestone that we define in this list, in this case just 2000 iterations, we're going to reduce our learning rate by multiplying it with this second argument. So in some cases that's really useful, especially if you're trying to train these things for a long time really well. You might want to implement some sort of learning rate schedule, but that one kind of a minor one. Now we're going to come to some of the meatier ones. So the next thing is, if you read the original paper, they show how you can just train these by starting with a random grid or an initial state, applying the update a number of times, comparing the output to your desired output, updating the parameters, and repeating. But what's tricky is that there's only so many updates we can do and still be able to trace back and have meaningful gradients. And so they can set up these systems, but they don't have long-term stability. So you can see in this little GIF here, they train for the first 50 or 100 iterations, and they do exactly what they're supposed to in that time, right? They produce the images, but they're not stable. And so if you continue, running these, over time they kind of collapse or go into these weird states. So that's not ideal. And to get around this, the system that they propose is to have a pool of grids at different stages. And in every kind of iteration, what we're going to do is sample from that pool. And some of these might be ones that have only had a few updates applied. Some might be fresh. Some might be fairly old and they've had many updates already applied. But we're going to take a sample from this pool. We're going to apply some additional iterations to them with our current cellular automata. We're going to compare how the outputs match our target. We're going to update the cellular automata accordingly. And then we're going to place those modified grids back in the pool. So this is their sort of algorithm. They show samples of this. This is while it's training. And we're going to do the same thing here. So this pool is our 256 grids. And then for every iteration, we're going to draw out some small sample from the pool. Occasionally, we'll refresh one with a new seed. Then we're going to apply some number of steps, right? In this case, a random number between 30 and 90, or 32 and 96. And we're going to apply that. We're going to apply our cellular automata for that number of times. Now we could do it like this. This code comes from their implementation, and instead they show that there's a sneakier approach that we can take, which saves memory and speeds things up. And so that's the third of four kind of key innovations in this training loop, is to use this thing called gradient checkpointing. And what gradient checkpointing does, there's a little explanation here. Instead of trying to keep all the gradients in memory for all of these multiple steps, we are going to run through, and then we're going to rerun the backwards pass for certain sections at a time, and use that to calculate the gradients kind of during this backwards propagation step. So it's kind of a nice optimization. It's in some sense trading additional compute for reduced memory usage. And in this particular example, it actually ends up faster, and it lets us use more, a larger batch size and still not run out of memory. It's a really, really cool little technique. This is one we haven't seen before. It's usually useful in cases where you have many, many updates applied. And so one big use is in reinforcement learning, where often you have an episode where an agent might take, hundreds or thousands of steps. Keeping track of all those accumulated gradients might be really, really tricky. And so gradient checkpointing would let you, rerun the forward pass as you trace back through that computational graph. Just save some memory and allow you to do longer episodes of training. So it comes in useful here as well. So that's innovation number 3. And then the final one, this comes down to this idea of, gradient explosion. You remember when we talked about training really deep networks, we had this issue where, a small error might be multiplied, and so some gradients might be really large by the time it's gone through, this whole chain of multiplications. And we have the same issue here where we have, up to 90 something steps being applied. We have the potential for these gradients to really get out of hand. And so if we didn't do anything about that, our updates with our optimizer, even with a very low learning rate, might be extremely large. They might push things out of any reasonable bounds. So if you left out this final gradient normalization step, you'd see the training was quite unstable, and you often struggle with nans in your loss and all these other issues. So this gradient normalization, it's just these, couple of extra lines of code. Once we've calculated the gradients with last.backwards, we're going to run through them and normalize them, right? And so this is going to take any that might be, outsized and having too big of an effect, and it's going to shrink them down into a more manageable range. Really, really neat trick. And with that, we get suddenly some somewhat stable training. So you can see here, this is a view of our losses. Now, because we're sampling from the batch, there's a bit of noise. But over time, the system learns to generate behaviors that start out from a smooth initialization and converge into some sort of semi-stable state where the texture looks kind of like the texture of the image, and it sort of matches the prompt, right? We said, what, green fireworks? Well, that looks like it's what we got. So that's fairly pleasing. And remember, this is something with very limited number of parameters, right? 8 hidden neurons or something like that. And it's able to produce these pretty cool patterns. So before we move on and try some more complicated networks, it's time to come back to that extra sort of secret function that I mentioned earlier, this print weights function. And this spits out this little bit of what looks like code. So to understand what this is, I'm going to copy and paste this. We have to do a brief aside, which is to talk about these things called shaders. Now, you may have heard of this in the context of games, right? Shaders are a type of program that runs really efficiently in parallel on the GPU. And so these are often used for any kind of computation that needs to be applied, per vertex in a mesh or per pixel on your screen. And so in particular, we're going to look at fragment shaders, and we're going to open this little link here, which is a website that lets you run these in the browser in real time. And if you switch over to the code here, we can copy and paste in those weights that were printed out in the notebook, and we'll see we get our green fireworks cellular automata running here in the browser in real time, and we can interact with it with the mouse. So I think this is a pretty neat trick. What I've done here is implement effectively the same computation that's happening in our Pytorch code, but this is in a specific language used for writing shaders. So we're sampling the 9 cells in the neighborhood, the upper left neighbor, top neighbor, the cell itself, putting those in a vector. Then we have our kernels, right? Identity, Sobel, Laplace, our activation function. And then for every kind of pixel on our output image here, we're going to find our coordinate. We're going to sample the textures around that coordinate. We're going to apply our filters. We're going to stack those all into our 16 inputs. And then we're going to run those through the first layer of the network, which is using these weights that we specify up at the top. So these are the weights from our neural network. It's using those learned weights, multiplying them, doing the dot product, putting them through the activation function, second layer, and producing a proposed update, which we can then, apply based on some randomness. And that's going to produce our output image. And so, yeah, pretty cool to see it running. Okay, I'm live recording the video and running a bunch of other stuff, but you can get this up to 60 frames a second quite stably. So yeah, I think these are pretty neat. There's a few demos down in the bottom of this notebook. So if you scroll right down to the bottom, you'll see some that you can copy and paste into this demo. And yeah, I think the effects are quite cool. I hope anyone watching this is as excited about these as I am. I think it's really great that we can feed in an image or a description and get out a shader that runs in real time that tries to replicate the look of our descriptions. So that's pretty neat little trick. And this is now an explanation for why we chose to have this particular set of constraints for our cellular automata here. Because for a shader on ShaderToy, you have 4-channel textures and fairly limited compute. And so by hard coding the filters, by having only 4 channels, we're able to squeeze it into this kind of real-time online demo. And you can see, yeah, there's some really cool ones to try at the bottom. Okay, but what if we don't have that constraint? What if we'd like to just see how complicated of a pattern these things can learn? We're going to basically copy and paste that code that we used earlier, but now we can specify the number of channels as an argument. We're going to explore using a larger number of hidden neurons in the hidden layer, but the rest is going to be pretty much identical. And so with this, again, we can feed in the same image of fireworks as before, a different description. And you're welcome to tweak all of these, try your own pictures, experiment with, assigning a higher weight to the clip prompt versus the style image and so on. But yeah, after a few thousand iterations training, we get a situation where, again, starting from, a pure grid and applying these random updates, we get these very, very lovely emergent patterns. And often some of them are quite dynamic and in motion. This one moves fairly slowly. But yeah, really, really beautiful and interesting. And I highly recommend, trying different prompts, trying different images, and just seeing what you can come up with. Okay, so one little addendum here. What if we want to start from something that isn't just pure randomness? You might want to start from an image or a particular pattern. So in this case, I show how we can patch the seed function of this neural CA class. And this applies even to ones that we've already created. So now we can use the same one that we trained above, but we're starting from, instead of a gray image, we're starting from a white little square. So that's just a little handy function. You might find that useful if you're trying to experiment with some different things. Okay, so we can hear the cry from the audience, where are our lizard emojis? So in this next section, this is sort of semi-final section, we're going to try and recreate some of the cool work done in this paper, but we're not going to do it with high attention to all of the extra tricks that they do, keeping track of which cells are alive and dead and so on. If you want that, here's an excellent 30-minute video recreating that really neatly in Pytorch, really great clean implementation. But in our case, all we're going to do is load an image, and we're going to tweak our training loop so that instead of a clip loss and a style loss, we're just going to, calculate our images after we've applied our updates, and then we're going to take the mean squared error between the outputs after our updates and our target image, right? So we're downloading a picture of an emoji, and then we're simply saying we'll penalize the network for not matching this image exactly. So very, very kind of minimal implementation here. But you'll see that it sort of works, right? We start from our new starting point that we defined just now. And after a few iterations or a few hundred iterations, with a bit of squinting, you can see the same lizard beginning to emerge and show itself there. So I choose to believe we haven't failed. We've just made art. If you watch the live lecture video, you'll see, I think we tried this again and got slightly better. But yeah, if you really wanted to, you should go and read the paper, see that other implementation, and see the ways that they make it even more stable. But I think it's pretty crazy that we can say, create this little neural cellular automata, start with random parameters, and just say we're going to penalize it if after a number of updates are applied to a grid, it doesn't look like a lizard, and it learns to self-organize without any global positioning information. All it gets is the information about each cell's neighbors. It's able to self-organize into a pattern that looks kind of like a lizard. So I think that's pretty cool. How are we doing for time here? Cool, I think that's about it, half an hour in. Now this section here has some ideas. They're by no means exhaustive, but I hope that this has inspired you to see, some of the potential of these really interesting systems, these differentiable self-organizing systems. So highly recommend, either picking one of these and exploring it, or trying your own ideas. What happens if you mix different automata in the same grid, right? You have a mask that determines which rule is applied. Can you start with an image and stylize it? Go and check out this guy on Twitter. He's been doing some really fun explorations of that, to take in an image and apply a cellular automata to stylize it. Could you drive some motion with video? Can you reward the automata for something that's more dynamic or less dynamic? What does a 3D version look like? What does it look like if you apply this at different resolutions? And so on and so forth. So highly recommend, just having fun with this. This is a really cool topic. It's really niche. It's not, currently used in any world-changing applications. But I think it's really fun. And I highly recommend you to go and play around. So if you're interested, the rest of the notebook is a couple of these experiments implemented. In this case here, just saying let's train a cellular automata. And then instead of just making a video, what happens if we start with a low resolution image, right? 16 pixels. And then we repeatedly apply our update. And whenever we hit one of these milestones, we double the size of the grid. And it turns out the result is these beautiful fractal images. We got people during the course suggesting prompts and making their own. And you're able to get, some really incredible, I think quite beautiful results, often very fractal in nature. And you can do the same thing to a video. You can start at really low resolution, apply the update a number of times, then double the resolution. Apply the updates, double the resolution. And then once it starts getting too big, you can just start cropping in and zooming in. And you get this kind of like infinite recursion of detail. I think really beautiful, really trippy. So highly recommend. Again, please train your own. Please show them on the Discord. I love seeing things that people make with this code. So if you come up with something particularly beautiful, do share it. If you train one of the simple CA that can be used as a shader and you find a particularly exciting results, again, send me the weights. I'll add them to this list here. Some of these have been submitted by members of the course. And you can try them out. You can also, click on this little fork button here if you have a Shader Toy account, and you can, permanently save your own shaders. We have some really fun ones that have been designed in the community. Cool, that's it for AIAIART Lesson 8. I hope you've enjoyed. We're going to take a break of a week or two before Lesson 9, and I think Lesson 9 or 10 might be the final one for Part 2. But I really hope you've enjoyed this. As always, if you have questions, comments, feedback, please do share. You're welcome to reach out to me on Twitter or comment on the YouTube videos. But the best place is probably to head over to our AIAIART GitHub, and then from there get the link to join our Discord, where we have ongoing discussion. You can talk about your own projects, get feedback, and it's really great for me to see if you're actually using this material and doing fun things with it. It always makes my day. So thank you so much, and we'll see you in the next video.